2023, final question, number 5. So, lactic acid has an association constant. Draw the conjugate base of lactic acid. So, it should be pretty clear. This is the acid functional group here. So, we're going to lose this hydrogen here. So, the conjugate base is like that. Then it says calculate the pKa. Well, I'm given the Ka value, so the pKa is just the same way you would calculate the pH, but now instead of the hydrogen concentration, we use the Ka value. So it's going to be minus log to the base 10 of 1.38 times 10 to the minus 4. So 1.38 times 10 to the minus 4 negative log answer gives me 3.86. Questions don't come much easier than that, which is why it's always important to read the whole paper through. Lactic acid is more acidic than propanoic acid, so this is more acidic than this due to a hydrogen bond which stabilizes it. So this is the conjugate base, and this is stabilized by a hydrogen bond. Draw out the structure of the conjugate base of lactic acid showing this hydrogen bond. So the hydrogen bond, there's 3 oxygens, only one of them has got a hydrogen bonded to it. So it has to be this hydrogen here that's hydrogen bonded. And it doesn't matter whether you hydrogen bond it to this or hydrogen bond it to this. I'm just going to draw it out like it is here. So I'm going to draw it OH to draw out the oxygen hydrogen bond. And then you draw out the rest of the molecule. And then I'm just going to show the hydrogen bond like that to remove any doubt. I'm going to write H bond like that. Okay. Now you can flip these two round if you want, but it doesn't matter obviously because this is going to be a resonance structure, so it works either way. Then we have this scary looking section here. So lactose is a disaccharide with the formula C12H22O11. In the first step of the conversion to lactic acid, lactose is converted into 2 monosaccharides. Fine. So the first of these questions is, how would you classify the reaction of lactose to form the 2 monosaccharides? So this is lactose, and I'm going to form 2 of these monosaccharides. Now the formula of all of these is exactly the same. They're just isomers. Okay, so it's just at each center, it's either coming in or going out. All right. So don't worry too much about the molecular formula for now. So to go from the disaccharide to monosaccharide, it should be fairly clear that it is definitely not elimination. We're not eliminating something. It's definitely not isomerization because we're breaking down a disaccharide into 2 monosaccharides. Condensation is, so hydrolysis, yes, hydrolysis is breaking the 2 apart. Condensation is the opposite, and then there is no oxidation or reduction because the reaction is happening here, right? So this link between the 2 sugar molecules, the 2 individual sugar molecules, is being broken. But either case, in the starting disaccharide, it's a carbon-oxygen bond and a carbon-oxygen bond, and then the resulting monosaccharide, it's still a carbon-oxygen bond. So there has been no oxidation or reduction. So the only thing that it's doing is hydrolysis. Fine. Then, write the names of monosaccharide sugars A and B that make up lactose. So the question is, essentially, which of these two are A and B? Now, for all you sugar chemistry fans out there, you may already know which 2 monosaccharides make up lactose, in which case you just work out which one is which. For those of you that haven't memorised the individual monosaccharides in disaccharides, we've got to do a little bit more investigation. So, as you can see, all of these are arranged in the same way. So we've got the 6-membered ring with the oxygen at the bottom. It's always 6-membered ring, oxygen at the bottom, 6-membered ring, oxygen at the bottom. And then we have the CH2 arm, okay, because there's 5 alcohols, right? 1, 2, 3, 4, 5. But this alcohol is on this CH2 arm. And the CH2 arm is always on the bottom left. Okay, so what I need to do is take this one, let's start with A, take this one and sort of get it into this orientation. Alright, so that's going to be a little bit tricky, so let me just draw it out and see if we can work this out. Now the bottom right is always just shown in the plane. Okay, that's fine. So what I'm going to do is I'm going to take this molecule and I'm going to rotate it around. Alright, 180 degrees. So I'm going to rotate the whole thing round. Okay, and then you'll see that this this arm here is going to be out. This one, sorry, in. This one out. This one in. This one out. Okay, does that match any of my options? Yes, here it is, glucose. All right, fantastic. So A is glucose. Then, so just if you weren't clear what happened there, I just took this ring and I rotated it around like that to match this orientation. This one is going to be a little bit more tricky because here, if I rotate it, it's not going to work. I'm going to have to flip it as well. So you can imagine what I'm going to do with this ring is I'm going to have to flip it over, because only that way can I get this arm on the left hand side. So let's try, and fingers crossed this should work. So if I flip, so I'm going to sort of like flip it along this axis here. All right, if I flip it, this arm is now going to be going away from me. This one that's coming out is also going to be going away from me. This one that's coming out is also going to be going away from me. This one that's going away from me will now be coming towards me. And then that one is never shown, so that one's just in the plane. So do I have one that looks like this? Yes, I do. Galactose. Okay, so B is galactose. So as I said, some of you may have known that lactose is made of glucose and galactose. If you didn't, that's how you'd work it out. Just take these, orient them the same way as this, and see how the stereochemistry lines up. All right, so quite an interesting start to the question. You may be, again, they seem to, this particular year, which is really a great year, I thought, for the Olympiad, they have these sort of questions that start in one direction and then just go in a completely different direction. So this was really nice. But then we have, the next part's fairly reasonable. Write an equation of the conversion of lactose to lactic acid. Okay, well, lactose, you'll remember I was told, is C12H22O11. So I can just write C12H22O11. And then I need to be a little bit careful. The conversion of lactose to lactic acid is accomplished by bacteria in a complex biochemical process. However, lactic acid is often the sole product. Now, the tricky bit of information is that we have to go back and remember that the first step of the conversion of to lactic acid, lactose is converted into 2 monosaccharides, and we said that that was a hydrolysis reaction. So it means that I'm going to be adding water, and then I'm going to get my 2 individual monosaccharides, but it says that the only product I end up with right at the end is lactic acid. So lactic acid is here, 1, 2, 3 carbons, C3, H, 1, 2, 3, 4, 5, 6, 6, O3. Okay, so lactose, hydrolyze, end up with lactic acid. Okay, and then we can balance it. Fingers crossed, it'll just balance nice and easy. So I've got 12 carbons here, I've got 3 here, so I'm going to put a 4 there, and hope that that's all I need to do. So I've now got 24 hydrogens. I've got 22 and 2 is 24, and I've got 11 and 1 is 12, and 4 and 3 is also 12. Fantastic. Okay, doesn't come much easier than that. Then we have many varieties of Swiss cheese. blah, 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 blah. This bacterium carries out the reaction of lactic acid to propanoic acid, ethanoic acid, carbon dioxide, and water. Write an equation for the production of carbon dioxide carried out by this bacterium. In the net reaction, lactic acid is the sole reagent. C3H6O3 becomes, and ethanoic acid and carbon dioxide are produced in equal amounts, but I have 4 products, so I'll write all of them out. Okay, so CO2, my carbon dioxide, and then the ones that are in equal amounts are carbon dioxide and ethanoic acid. Ethanoic acid, formula of ethanoic acid is CH3COOH. I'm going to write the molecular formula to make it easier. So that's C2H4O2. C2H4O2. Just makes it easier to count. Plus propanoic acid. Propanoic acid I'm given here 1, 2, 3. So C3, 1, 2, 3, 4, 5, 6, H6O2. C3, H6O2, and the final one was water. And then I have to balance it, but I have to keep these two in the same quantity. So, for a balancing equation like this, I just use a bit of trial and error. So, I've got 3 carbons here, I've got 1, 2, 3, 4, 5, 6. So I could try putting a 2 here. So if I had a 2 here, that would be 12 hydrogens. 4 and 6 and 2 is 12, so that would work. If I have 2 here, I have 6 oxygens. And I've got 2 and 2 is 4, 2 is 6 and 1 is 7. So I can't have a 2 here. Alright, so let's try a 3 here. So if I do I'm going to start writing these in now. Otherwise it's going to get too complicated. So 3 gives me 9. I've got 1, 2, 3, 4, 5, 6. So I need 3 more. But these two have to be kept in the same ratio. So if I were to double this one, I'd have to double this one as well. Or I can double this one. Let's go with that. So I've got 9 carbons. 1, 2, 3, plus 6 is 9. I've got 18 hydrogens. 4 and 12 is 16, and 2 is 18. And then I've got 9 oxygens. 1, 2, 3, 4, plus another 4 is 8, and 1 is 9. Oh, okay, so there we go. Is there an easier way to do that balancing equation? There must be. It's probably something there that I'm not quite seeing that would restrict me from. Anyway, I'm not going to think about it. If you want, you can think about it in your own time, but just a bit of trial and error should get you through there quite easily. So assume during fermentation at 21 degrees C a spherical bubble. All right, so now we're going to get into a bit of a number crunching situation. Spherical bubble of diameter. Whoa, be careful. They love to do that. They love to give it the diameter and ask you to work out a volume. And everyone just puts the diameter straight in without dividing it by 2. Tricky. Okay. Calculate the volume. Well, I know the volume of a sphere because I'm told the volume of a sphere, 4/3 pi r cubed. So let's just go ahead and do that calculation. So volume equals 4/3 pi r cubed, which is 4/3 times pi times my radius. Now, it tells you it wants it in meters cubed. Obviously, why wouldn't you want it in meters cubed? That makes the most sense, right? The diameter is 1.5 centimeters, which equals 0.7. So the radius is 0.75 centimeters. But in meters, I'm going to divide it by 100. So 0.0075 meters. So 0.0075 cubed. 0.0075 cubed times pi times 4 divided by 3 gives me 1.76, no, 1.77 times 10 to the minus 1, 2, 3, 4, 5, 6, minus 6 meters cubed. Okay, that was fairly painless. Then it says, assuming the bubble is pure carbon dioxide at atmospheric pressure, calculate the mass of lactic acid. So, assume it's pure CO2, but calculate the mass of lactic acid, which was fermented by the bacteria to produce the bubble. For the calculation, assume that CO2 obeys the ideal gas law. Excellent, no problem, I can do that. So, what I need to do first is work out my moles of CO2. So my moles of CO2 is going to be equal to PV over RT. My P is 101325. Now this is actually why they wanted you to calculate the volume in meters cubed. It wasn't just an annoying thing, it means that now you can just put the value straight into this equation. 1.77 times 10 to the minus 6, because if you'd worked out in centimeters cubed, you wouldn't be able to use it with this value with the pressure. You'd have to do another unit conversion. Divided by RT, 8.314, multiplied by 21 degrees plus 273 is 298. So if I do 101325 multiplied by 1.77 times 10 to the power of minus 6 divided by 8.314 divided by 298 gives me 7.24 times 10 to the minus 5 moles. And then that's of CO2, right? So that's my moles of CO2. So my moles of lactic acid equals my moles of CO2. The equation's here. My moles of my CO2 is produced from lactic acid, so 1 mole of this requires 3 moles of this, so it's that times 3. So I can times that by 3 to give me my moles of lactic acid, and then I'm going to work out my mass is going to be my moles of the acid multiplied by the molar mass of the acid. And the molar mass of the acid, so lactic acid is going to be that times C3. Oh, I should have worked this out separately, shouldn't I? Oh, this could be risky. 12.01 plus 6 times 1.08 plus 3 times 16, 48. Fingers crossed. 0.0195 plus the MR. So I get 0.0196 grams. Excellent. So just a bit of light stoichiometry, really, nothing too taxing. Then we get down to business. So, note the statement of cheese is CH, bit of Olympiad humour for you there. Carbon dioxide dissolved in cheese can exist in 2 forms: dissolved gaseous carbon dioxide, CO2, cheese, or dissolved hydrogen carbonate, HCO3-, cheese. At the end of the fermentation, concentration of carbon dioxide in the cheese and the concentration of the hydrogen carbonate in the cheese sums to this value. The pH is this value, and my equilibrium constant is this value. And it asks me to work out the concentration of carbon dioxide. Okay, so I've got carbon dioxide here, and I've got carbon dioxide here. I've got HCO3- twice, and I know the H plus because I can get it from the pH. So let's just write out all the information that I've got, because this can get away from us quite easily if we're not careful about it. So number 1, my equilibrium constant I'm going to dispense with the state symbols just to make it a little bit cleaner. My equilibrium constant is 4.47 times 10 to the minus 7. The sum of the concentration of CO2 and hydrogen carbonate is 3.7 times 10 to the minus 2, and my H plus concentration is 10 to the minus pH 5.2. So 10 to the minus 5.2 is, let's call that 6.3 times 10 to the minus 1, 2, 3, 4, minus 6. So those are my 3 pieces of information. And I need to find CO2. So, what's the best way to do that? Probably, if I rewrite this in terms of CO2. So let's do that. So my CO2 concentration, put the C, is H plus HCO3 minus divided by 4.47 times 10 to the minus 7. And then I can substitute in HCO3 minus by rearranging this. HCO3 minus equals 3.7 times 10 to the minus 2 minus CO2. And I can put H plus in as well. So I'm going to get 6.3 times 10 to the minus 6. That's that into there. Multiplied by 3.7 times 10 to the minus 2 minus CO2. Should have just changed that for X. That's that into there. Divided by 4.47 times 10 to the minus 7. I'm going to change it for X. This is too much. I'm also going to get a different coloured pen to make myself feel better about it. So let's switch this for X and this for X. Solve for X. So can I do it within the box? 4.47 times 10 to the minus 7 X equals these two multiplied together. So 6.3 times 10 to the minus 6 times 3.7 times 10 to the minus 2 is 2.331 times 10 to the minus 1, 2, 3, 4, 5, 6, minus 7 minus 6.3 times 10 to the minus 6 X. And then that is the equation I solve for X, which is pretty easy to do. Okay, so I can add this to both sides. So I get 4.47 times 10 to the minus 7 plus 6.3 times 10 to the minus 6 gives me 6.747 times 10 to the minus 6x equals 2.331 times 10 to the minus 7. Tiny writing here. So then x equals 2.331 times 10 to the minus 7 divided by that, which is 0.035. So is that an answer that makes sense? It's difficult to say for certain. I mean, you could put it back in and double check you've done the arithmetic right, but on this occasion I have done the arithmetic right, so I'm not going to bother doing that. But as you can see, again, classic Olympiad, none of it's that difficult, right? You know, it's for this occasion, it's very, very straightforward maths, but it's just doing a lot of it with lots of exponents and making sure you don't make any mistakes as you go through it. Anyway, so if you thought that was tricky, let's have a look at the next part. We now examine how CO2 bubbles of a certain size are formed in the early stages of fermentation. Suppose a bubble of radius r is in contact with a fixed volume of cheese, VCH, at temperature T. The pressure of CO2 in the bubble, PB, the pressure, is related to the concentration by a constant. So the concentration of the cheese, sorry, the concentration of the carbon dioxide in the cheese is related to a constant multiplied by the pressure in the bubble. And then in the table, in the answer booklet, tick which expression gives the molar amounts of CO2 gas. So the concentration of CO2 in the bubble. CO2 cheese, the concentration of cheese in here. And the HCO3 minus cheese, the concentration of HCO3 minus dissolved in the cheese as well. Whew. Okay, so where do we start? I think the easiest place to start is going to be with our moles of CO2 gas. Now, the moles of CO2 gas is not going to be related to a concentration, because this is the concentration of the CO2 in the cheese. But I want the moles of gas in the bubble. And the moles of gas in the bubble is just going to be based on PV equals nRT. Right? So it's going to be PV over RT. Okay? Now that's not any of my answers, unfortunately. But you can see a lot of my answers have got the 4 pi r cubed over 3, which is the volume of the sphere. So I can replace my V. So I can say I've got my P. No, that should be PB, because we're talking about the pressure in the bubble. Multiplied by 4 pi r cubed over 3 RT. So all I've done is I've replaced volume with the equation for the volume of the sphere. Is that one of my options? Yes, it is. Fantastic. Okay. All right, 1 out of 1. Let's do the moles of CO2 cheese. Well, I know that, let's just cordon that off. I know that the concentration of CO2 in the cheese is my Henry's constant multiplied by the pressure of the bubble. So the moles, to go from concentration to moles, you remember, well, it's very simply C equals N over V. So this is going to be, I shouldn't have written this here, the moles is going to be my concentration, KHPB, multiplied by the volume. Okay, and because it's the concentration in the cheese, it's multiplied by the volume of the cheese. Is that one of my answers? Yes, it is. That one was even easier. All I did was convert a concentration into a molar value by multiplying it by the volume. And then the last one. Got a feeling this one's not going to be so easy. My moles of HCO3 minus in the cheese. Okay, so where can I get my HCO3 minus from? Well, I've got 2 expressions that I've got HCO3 minus in. I've got my equilibrium constant expression, and I've got this sum of carbon dioxide and carbonate ion. Now, none of these has got a plus or a minus in it, right? So I'm not going to use this one. I'm going to use the equilibrium constant. So let me rearrange that. Okay, so I can work out the concentration of HCO3 minus as the equilibrium constant multiplied by the concentration of CO2 in the cheese divided by the concentration of H plus in the cheese multiplied by the concentration of... Oh, I've completely lost myself now. What I'm trying to do is rearrange this equation. Okay, so let's just double check. HCO3 minus is... No, that's it. Okay, so I've got there. That's it. That's why I was confused. So I'm there. Now, does that look like any of my answers? Well, these two have both got the equilibrium constant in. And they've both got 10 to a pH. Now I know that this is going to become K CO2 cheese divided by 10 to the power of the minus pH, which is the same as K CO2 cheese times 10 to the pH. So I see that it's going to be... Oh no, these have both got 10 to the pH. So it's not these two, so it's one of these two. Alright, so you see what happened there. Because I've got my H plus in the denominator, I've got 10 to the minus pH in the denominator, but I can just switch the sign and put it up top. So it's one of these two. So then all I need to do is just take my CO2. Oh no, hold on, let's not get carried away here. So remember, I'm just going to write this here again, HCO3 minus, so this is my concentration, and I want a value for the moles. So that's going to be, well, let's do it. Let's do the whole thing. It's my equilibrium constant multiplied by my concentration of CO2, which is the Henry's constant, multiplied by the pressure of the bubble, multiplied by 10 to the power of the pH, multiplied by the volume of the cheese. And there, the answer reveals itself. Okay, remember, it's that final step where I go from concentration to molar quantity. I mean, this is, you know, I guess this is, it's just arithmetic applied to a chemistry situation. But, yeah. Don't worry, it gets even more complicated on the next part. So, the sum of the molar amounts in H, oh, we're not done, is constant and labelled eta. And the pressure inside the bubble is modelled by this equation. So the pressure inside the bubble is atmospheric pressure plus gamma over R, where gamma is a constant. Okay, fine. Substituting this expression for the pressure inside the bubble, express the sum of molar amounts as this. Okay, fine. So let's just see what the question is asking us. Express the sum of molar amounts. And it says here the sum of the molar amounts is labelled eta. So let's do it. Eta equals, and then I have my molar amounts. This one. PB times 4 pi r cubed over 3 RT plus this one, KH dot PB dot VCH plus this one, equilibrium constant. Don't get confused, all these K's, big K, little k. Put two of them right next to each other, look. Big K, little k. PB, 10 to the pH, VCH. Alright, so there's my equation. And it wants me to express it in this form here. Okay, fine. Well, P-ATM plus gamma over R is just a substitution of PB. So I can collect all the PBs together. and I've got PB, PB, PB. So I'm going to factorize out all of those. So eta equals 4 pi r cubed over 3 rt plus kh vch plus k little k 10 to the power of ph vch. So it's all of that multiplied by PB. Okay. And then it wants me to collect the r cubed term. The r cubed term is here. So fine, okay, I can do that. So eta equals, let's have this term, kh dot vch plus this term, k, kh, 10 to the ph, vch, plus 4 pi over 3 rt r cubed, multiplied by PB, and now I can make that other substitution, which is P ATM plus gamma over R. Okay, and we're done. But now I would just give A and B. So I would just say A is this bit here, and you can factorize that as well if you wanted to. I've got a KH and a VCH, so I can do 1 plus K 10 to the PH. And my B is just the coefficient of the R cubed, which is 4 pi over 3 RT. And then it goes on. This equation gives the bubble size R, but it's too complicated. Ooh, you're telling me. Instead, we use the smallness of this value compared to P ATM to approximate it with a simpler equation. This is the simpler equation. It doesn't look simpler, but okay, fine. At this stage of the fermentation, you've got A, B, eta, gamma. Okay, so I've got a B, I've got gamma, I've got eta, I know the atmospheric pressure. I'm trying to work out R, but I've got a D. But it's okay, because I've got D over here, again, in terms of eta, the atmospheric pressure, and A. Fun times. Okay, so calculate the two possible values of R. What does that mean? It means that I'm going to get a quadratic. And you can see that I must get a quadratic because I've got an R here and an R here. So essentially what I need to do is get this into a quadratic form and then solve it for R. Alright, now, strategy. I've got a D here and I've got a D here, and I've got a separate equation for D. So, first thing I'm going to do is I'm going to work out D and hope for the best. So D equals eta 2.35, and this you want to be nice and neat because this, they give you a massive box, right? Big huge box. It's probably not going to be big enough. Okay, let's try and keep it all within the margins. 2.35 times 10 to the minus 4 divided by atmospheric pressure 101,325. Subtract A, 1.7 times 10 to the minus 9. Okay, that's my value of D. 2.35 times 10 to the minus 4 divided by 101,325. Subtract 1.7 times 10 to the minus 9 gives me 6.19 times 10 to the minus 10. Okay. Next, I think before I put any of the numbers in, I want to do some rearranging. So let's write out the equation again. I always just like to do that, otherwise I don't really know where I'm standing. So D over B to the power of a third. Oh, disgusting. 1 minus gamma eta over 3 P ATM squared D times by 1 over R. And what I'd really like is to have this. I'd like to have this in terms of R, wouldn't I? So let's multiply this out. So I'm going to get R equals that times 1. So it's going to be D over B It's probably, if someone is better at maths or algebra than me, probably an easier way to do this. Minus d over b to the power of a third multiplied by gamma eta over 3p squared d times 1 over r. And then I can multiply through by r. So I get my r squared that I was anticipating, d over b to the power of a third r minus d over b to the power of a third times by gamma eta over 3p squared d. And then I think now is the time to work out these numbers. So it's going to be r squared equals d over b. So d is up here, 6.19 times 10 to the minus 10. Divide by b, which I'm given as 1.75 times 10 to the minus 3. All to the power of 1 divided by 3, which is 0.00707r minus, now this is the same thing again, I've already got that in the calculator, fantastic. So that's that, so I multiply it by gamma, 9.28, multiply it by eta, which is 2.35 times 10 to the minus 4, divide it by 3, divided by the atmospheric pressure squared, 101325 squared, and divide it finally by d, my number up here, 6.19 times 10 to the minus 10. The possibility for incorrect use of the calculator is phenomenal. 8.09 times 10 to the minus 1, 2, 3, 4, 5, 6, 7, count the zeros, times 10 to the minus 7. There we have it, that's my equation. Now I need to solve. So r squared minus 0.00707r plus 8.09 times 10 to the minus 7 equals 0. So r equals plus 0.00707 plus or minus the square root of, let's just work it out, b squared, 0.00707 squared, take 4 times 1 times 8.09 times 10 to the minus 7. The square root of that, 0.0000467 divided by 2. Okay, do it. So the square root of that, I'm just going to write separately, is 0.00684. So then I have 0.00707 plus 0.00684 divided by 2 is 0.00696, or 0.00707 take 0.00684 divided by 2 is 0.000115. Okay. And then the very last thing, it says, calculate the two possible values of r, done, that satisfy the simplified equation and state which is the correct physical solution consistent with gamma over r being small compared to p ATM. Now the easy mistake to make here is to think that because we want it to be small, that you go for this one. But that would be wrong, because gamma is 9.28. So I've got two options. I've got 9.28 divided by 0.00699, or I've got 9.28 divided by 0.000115. And you can see, because this number is smaller, this whole fraction is going to be larger. So the one that I select is the larger one. However, I paused for a moment because I don't have units on my radiuses, which is a disaster. But I can just take a quick look and I can see that these numbers are all in meters. So I'm just going to add in meters here. Does that make sense for meters? If I had a bubble which was 0.007 meters, times it by 100, 0.7 centimeters seems like the kind of size of bubble you would get in a piece of Emmental, so I'm happy with that. That seems like a good answer. Alright, so a huge amount of crunching numbers there. That is by far the longest question in terms of time, because you have to do just so much of this working out. You know, you'd really, to get through that in the test, you really got to work at speed and get it all right. But honestly, fantastic paper, really very enjoyable, lots of really interesting questions, covers lots of chemistry, and all, you know, generally fairly accessible. So hope you enjoyed it.